Okay, what's up everyone? Welcome back. I hope you had a wonderful spring break. Today we're going to continue our discussion of the different forms that you can put the matrix of an operator into. That is, if you have a finite dimensional vector space and a mapping that is linear and sends that vector space to itself, then if you choose a basis, you can take the matrix of that operator with respect to that basis, both for the domain and the codomain, since they're the same. Okay, cool. So what types of matrices you can get out from this tell us things about the operator. That's been the theme we've been exploring lately. So last time we talked about upper triangularity and what this means for us. Now we're going to talk about perhaps the nicest kind of upper triangularity that could possibly occur, and that is diagonality. So section 5D, diagonal operators. Here's the idea. A diagonal matrix is just an extremely nice square matrix. A diagonal matrix is just a square matrix that has zeros everywhere except on the diagonal, potentially. It could have zeros in the diagonal, but that's the only place where you have any option to have anything other than zeros. All right, cool. Basically, think of it this way. A matrix is diagonal if both the matrix and its transpose are upper triangular. That's the way to think of it. So, an operator on a vector space V is said to be diagonalizable if there is a choice of basis that gives that operator a diagonal matrix when you take the matrix of that operator with respect to that choice of basis. All right, cool. Basically the same kind of thing as before. So basically, if you want to think about it this way, here's how you can do the whole thing. An operator on V is diagonalizable if you can find a basis that makes it upper triangular, and recall this really quick, remember, when you found the dual basis corresponding to a basis, then the dual map of that linear map with respect to the dual basis was just the transpose of the original map. So what's going on here is we're saying that an operator is diagonalizable if you can find a basis that makes it upper triangular, that makes the matrix of that operator upper triangular, and is such that the dual map is also upper triangular with respect to the dual basis corresponding to that same basis. Maybe that feels like a bit of a mouthful. We'll revisit that perspective later, perhaps not today, but in case it does help, it's a good way to think about why this might be useful. Another way to see it, if maybe this makes it a little bit more helpful, is that diagonality is extremely nice. So notice, if T is diagonalizable, then T of VK, where VK is the basis here, is just equal to MT, in particular, it will be what? KK, VK, for all VK in the basis V1 through Vn, diagonalizing the matrix of T. That is, think of it this way, you've just got a square matrix, you've got your entries along the diagonal that are stars, I'll put those as stars, so there's something, they could be non-zero, everything else is zero outside of that. Okay, cool. Now if you put like a column vector here, and you just had like a 1 in one spot, zeros everywhere else, then that's basically the same thing as taking the matrix of a basis element, that is the matrix of the basis element corresponding to the place where you put the 1. This will just grab the corresponding star entry there times that 1. Get what I mean? So whatever the entry is here, let's call it like AII. You'll just get back AII times this thing here, yeah? Get what I mean? So, in this sense, diagonal matrices are extremely nice because, with respect to the basis elements, it acts just like multiplication, the simplest possible linear map, scaling. All right, cool. So, why will we end up caring about this? Well, one, for the reason we just talked about, that there's a nice way to interpret this, but the other one is because of eigenspaces. So if you've got T, an operator on a vector space B, V, and lambda, a field element, we're going to define the eigenspace of T corresponding to lambda as the subspace, which we'll represent by E lambda T of V, that is just the null space of T minus lambda I. Okay, so think about it like this. We have two different choices. One, we could define eigenspaces with respect to eigenvalues of an operator. This unfortunately means we have to know whether or not a value is an eigenvalue. Or we could define eigenspaces with respect to any old field element, which is what we're doing here, and then the eigenspace will be non-trivial only when that value is an eigenvalue. So think about it like this. We know that the null space of T minus lambda I is non-trivial precisely when lambda is an eigenvalue of T. Okay, cool. So if E lambda T is not equal to 0, the trivial subspace, this happens if and only if lambda is an eigenvalue of T. Okay, so the way we've defined things, and this is maybe confusing, what I'm trying to highlight is that we've defined things so that we have eigenspaces for every single scalar lambda in our field. That is, it's not the case that whenever you see an E lambda T, you can instantly assume that lambda is an eigenvalue of T. The way we're defining things is that the only times you can assume that lambda is an eigenvalue of T when you see an E lambda T is if you know that E lambda of T is not the trivial subspace with just the 0 vector in it. Okay, so we defined eigenspaces so we can talk about them with respect to any scalar, and we did it so that the only times we get a non-trivial outcome from that is when the scalar is actually an eigenvalue. All right, it's a little bit more confusing in that way, but a tiny bit of overhead just makes a lot of theorems a little bit easier to state. Let's go to our first one, which isn't actually too bad. So here's the idea. Let's suppose that T is an operator on a vector space V, and lambda 1 through lambda m are distinct, very important, eigenvalues of T. Then the sum of the eigenspaces of T corresponding to these distinct eigenvalues, lambda 1 through lambda m, so this is a sum of subspaces. This big sum here is a direct sum. Oh, nice. And as a consequence, if V is finite dimensional, then the dimension of the sums of these guys is less than or equal to the dimension of V. That actually will turn out to be an incredibly obvious consequence once we do our proof, and we'll talk about it more then, but let's prove this first part just to get started. So, to show E lambda 1 T plus dot 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 all the way down through E lambda m T, that is the sum of these eigenspaces corresponding to distinct eigenvalues of T, is a direct sum. I'm going to zoom out a little teeny tiny bit to give myself a bit more room to write. Suppose V1 plus dot 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 all the way down through Vm is equal to 0, where Vi is in the eigenspace corresponding to lambda I for T, with I in, I'll write in instead of equal to just for clarity, the set 1 through m. Okay, now, since any non-zero Vi is an eigenvector. Terrible handwriting there. Eigenvector of t corresponding to the eigenvalue lambda I. This is a sum of distinct, or of, I will say this, this is a sum of 0 or more eigenvectors corresponding to distinct eigenvalues of t. But eigenvectors corresponding to distinct eigenvalues are linearly independent. So this sum must only consist of zeros. That is, if you look at this sum up here, any part of it on the left-hand side that has terms that are other than 0, well, that's a sum of eigenvectors corresponding to distinct eigenvalues. But those guys are linearly independent, so they never sum up to 0. So this sum must have 0 non-zero terms, i.e. vi equals 0 for I in 1 through m. Oh, okay. Hence, the sum is direct. Why? Because the only way to write the 0 vector is as a sum of zeros. Okay, cool. Consequently, think about this. Dim v, this is greater than or equal to the dimension of, oops, there we go. E lambda 1, let me zoom in here a little tiny bit, make it easier to see. Consequently, E lambda 1 t, okay, plus dot 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 all the way down through E lambda m t. After all, this thing is a subspace, so it's a subspace of V, so the dimension of a subspace of V is less than or equal to the dimension of V. All right, but this is a direct sum, so this is in fact equal to the dimension of E lambda 1 t plus dot 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 all the way down through the dimension of E lambda m t. Oops, I put my parenthesis on the wrong side right there. Sorry about that. E lambda m t. Ah, cool. Okay, so we're just using directness to say, hey, the dimension of a direct sum of subspaces is the sum of the dimensions of those subspaces. We talked about this way, way back at the beginning of the class. So not too bad. The whole gist of everything we're doing here is just that, hey, if you take distinct eigenvalues and you sum together the eigenspaces corresponding to those eigenvalues, the only time you can get 0 as a sum of vectors, each coming from the terms in that sum of subspaces, the only way you can get 0 is by taking all of those vectors to be 0, since eigenvectors corresponding to distinct eigenvalues are linearly independent. This just means that this sum is direct, and as a nice consequence, since the dimension of a direct sum is the sum of the dimensions of the terms in the direct sum, this just means that the sum of the dimensions of the eigenspaces corresponding to distinct eigenvalues of an operator is less than or equal to the dimension of V. Nice. Okay, this is just a good sign for us. That's really the whole point of this piece right here. This is good. Why? This is a good sign if we want to understand what t does by breaking it down into what it does on eigenspaces. That is, we want to understand the potentially complicated operator t by saying, hey, let's find low-dimensional invariant subspaces of t on which t behaves very simply. In particular, we'll find invariant subspaces where t acts like multiplication. That's the entire idea of eigenvalues and eigenvectors. This is looking good because it says that if you take distinct eigenvalues, then these invariant subspaces where t acts like multiplication, these guys, sum them together, you don't have too much information. That's the nice way of saying it. There's no big weird overlap. This is a true no overlap breakdown of v into nice little pieces. We don't yet have the ability to say something like the sum of all of these eigenspaces is itself v, but it is at least some proper little chunk of v, and that's kind of good. So let's go a little bit further and let's see what else we can do with this particularly nice kind of form that a matrix can have. Okay, here's the next little bit. So here's good. We're gonna resolve the thing I kind of hinted at just a moment ago when we looked back over here and I said, hey, we can't exactly break down v yet into a sum of eigenspaces, but the key part there was yet. So here we'll show that you indeed actually can in this particular case. So, and sorry that this lecture, I hope my voice isn't too rough right here. I've been kind of sick over the last weekend, so I'm dealing with a hoarse voice at the moment. So here's the idea. We're going to describe a bunch of conditions that are equivalent to diagonalizability, and these are great conditions. Okay, so if v is finite dimensional and t is an operator on v, then let's let lambda 1 through lambda m be the distinct eigenvalues of t. Distinct here being the opportune word. Then the following things we're going to say are equivalent. T is diagonalizable, that is, there's a basis with respect to which the matrix of t is diagonal. There is a basis of v consisting of eigenvectors of t. So v has a basis of eigenvectors. V is a direct sum of these eigenspaces corresponding to distinct eigenvalues of t, and the dimension of v is precisely equal to the dimension of these eigenspaces corresponding to distinct eigenvalues, the sum of those guys. Okay, cool. Let's prove it. Let's think through this. So, to start with, let's do A implies B. And we'll talk about this as we go. So for A implies B, suppose T is diagonalizable. Let V1 through Vn be a basis of V such that the matrix of T with respect to this basis, I'll write it in the following way, is just lambda 1 on down through lambda n, and then zeros everywhere else. Okay. So these lambda 1s through lambda n's are just field elements. I'm not yet saying they're eigenvalues, but I want to point out the following. Then, by the definition of the matrix of T, T, here, right, got a little T of VK is equal to the matrix of T's kth entry, in fact, of VK, which is just a fancy way of saying lambda k VK here, since we've written the matrix of T in this form. Notice I'm not writing the other terms because all the other terms are 0. TVK is a linear combination of V1 through Vn, and the coefficients in that combination come from the kth column of the matrix of T. The only term in the kth column that is non-zero, potentially, is the kth term, the term on the diagonal. Okay, we've already labeled those as lambda k here, in this case. So this says that T of vk is lambda k vk. So lambda k is an eigenvalue of T, and since vk, or I should say since vk is not equal to 0, and vk is then an eigenvector. So if T is diagonalizable, then you can find a basis such that the matrix of T is diagonal. Okay. And we just showed that every element in that basis is an eigenvector. So A implies B. All right, cool. Let's do B implies C. So this is actually pretty straightforward so far. If T is diagonalizable, then you can find a basis where all of the basis elements are eigenvectors of T. All right. Now, if we have a basis consisting of eigenvectors of T, suppose V has a basis of, I'll say consisting of eigenvectors of T, what we'll show is that V is a direct sum of the eigenspaces corresponding to distinct eigenvalues of T. Okay. Now, then, every V and V is a linear combo of eigenvectors. Terrible handwriting today. Sorry, guys. Of T. Okay. Not too bad, right? Thus, it is a sum of elements from E lambda 1 T through E lambda m T, where lambda 1 through lambda m are all the distinct eigenvalues of T. Oh, okay. So each eigenvector must belong to some eigenspace, right? It must be associated to some eigenvector, or eigenvalue, right? Okay. This means that I can write every vector as a linear combination of eigenvectors, hence as a linear combination of things belonging to eigenspaces. Oh, okay. Cool. Now, this lets us say that V is equal to E lambda 1 T plus dot, 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 all the way down through E lambda m T. But wait a second. Didn't we just show that the sum of eigenspaces corresponding to distinct eigenvalues of T is a direct sum? That was the first thing we showed. And by our previous result, this sum is direct. Oh, nice. Okay. Bam. So we did A implies B. We did B implies C. Let's do C implies D. This is not too bad, because once we've got C implies D, this one is extremely straightforward. So C implies D. Suppose V is a direct sum of the eigenspaces of T. Then we have our result. That is, I'm not even going to reference this one, the specific number for it, because it was so long ago. This was the very beginning. We just know that the dimension of V is equal to the dimension of this sum. So E lambda 1t plus all the way down through E lambda mt. So I'm taking the dimension of this whole thing, which is just equal to the sum of those dimensions. That is, you can split up dimensions over a direct sum. E lambda 1t plus all the way down through dim E lambda mt. Bam. Okay, cool. Now let's do D implies A. This is the only hard part of this. So we've got C implies D, and now we're going to wrap around here and do D implies A. And just by following the path, we've now proved that all of these are equivalent. So we're going to suppose that the dimension of V is is the sum of the dimensions of the eigenspaces corresponding to distinct eigenvalues of T. And then we're going to say, hey, let's show that means that T is diagonalizable. Okay, so suppose dim V is equal to the dimension of E lambda 1t plus all the way down through dim E lambda mt. Okay. Take a basis for each E lambda I t and put them all together as a list v1 through vn with n equal to the dimension of V. We can do this since we know that each one of these guys has a basis of, well, its dimension. And so if you put all these together, you get something that's the length of a basis for V. That is the dimension of V. Okay, cool. Suppose A1 through AN are field elements such that A1 V1 plus all the way down through AN Vn is equal to 0. Write UK equals, I'll say it this way. Write UK for the portion of the sum belonging to E lambda k t. So I'll write this one, u1 plus um equals 0. So you've got v1 through vn. Some of these, it might be like v1, v2, and v3 all belong to E lambda 1t. So to that first eigenspace. Since we're just taking a basis for each one of them and we're putting them all together into a big long list. All right, so just grouping the chunk together that comes from each eigenspace along with its coefficients, we can rewrite this as a sum of things from each one of those. Okay. Since eigenvectors corresponding to distinct eigenvalues are linearly independent. Move that over, sorry. And since each UK is an eigenvector if UK is not equal to 0, this must mean UK equals 0 for K between 1 and M, right? Since any non-zero terms in this sum right here must be eigenvectors, And then we would have a sum of eigenvectors corresponding to distinct eigenvalues, and there's no way you can get out 0 from that, since they are linearly independent. Oh man, this means they all have to be 0. So, all the AI must be 0 as well, and V1 through Vn is a linearly independent list of length dim V, and hence a basis of V. Done. Whoa, okay. Whole business of this right here is just that, hey, start out with the dimension of V equal to the sum of the dimensions of the eigenspaces corresponding to distinct eigenvalues of T. We grab a basis for each one of those eigenspaces, put them all together into a long old list. Okay, now if we group together the pieces from each one of the eigenspaces, then we can rewrite a linear combination of these elements in the list as a sum of elements belonging to each eigenspace. But eigenvectors corresponding to distinct eigenvalues are linearly independent, so all of these pieces of the sum from each eigenspace have to be 0, meaning that the terms you put together to get that sum must be 0. Oh, okay. So this is a linearly independent list of the length of a basis, and that means that it is a basis. Now, the piece maybe here that I might have glossed over is why all these AI must be 0 as well. Is everyone seeing that? The main reason for it is that the AI correspond to a little chunk of this linear combination consisting of the portion of the list, the next to the pieces next to the V's belonging to the kth eigenspace. That is what the UK piece is, right? Now, for each one of these little eigenspaces, we're grabbing a basis and we're putting it all together. So each of these UKs is a linear combination of basis elements for the kth eigenspace, right? Oh, okay. So how can you get 0 out as a linear combination of basis elements? Only by taking all of the coefficients in that combination equal to 0. That is why all of these AIs have to be 0. So all of these guys have to be 0 because these V's are each coming from bases, or they are basis elements for an eigenspace. Okay, cool. Well, we just did this crazy long little theorem right here that shows all of these things are equivalent to diagonalizability. Basically, the big takeaway from it is that diagonalizability tells you that you have a basis of eigenvectors. So the only time that you can say that you have a basis of eigenvectors is if you can write the matrix of that operator as a diagonal matrix. It's super nice. It also says that maybe having a basis of eigenvectors is something that's a little bit too strong for us to hope for. We might have to explore a slightly more general alternative, which we will. But for now, it says, hey, we've got an answer to our question. When can we break down our vector space into one-dimensional chunks where our operator, that's potentially very complicated on the whole space, just acts like the simplest possible operator on each of those one-dimensional chunks? That is the multiplication operator. That is scaling, right? The answer is done. The answer is precisely when you can find a diagonal matrix for that operator with respect to some basis. That is when you can diagonalize that operator. Okay, cool. There's a nice little consequence to this thing, which says the following. That is, if V is finite dimensional and T is a linear operator on V, and it has the dimension of V distinct eigenvalues. So if you have as many distinct eigenvalues as there are elements in any basis of V, then T is diagonalizable. So this may seem like something that's a little bit strange and hard to get to. how do we know we have a basis of eigenvectors? Well, we know it happens if we have a way to turn the matrix of T diagonal, but that might be hard to know. One really easy way to know it is if you have enough eigenvalues. So if you have at least as many eigenvalues as the dimension of your space, there's always a way to do this. Pretty cool. All right, let's see if we can do anything else today. Okay, here's the last thing we'll do today before we wrap it up. Then we'll do a little tiny bit more about diagonal matrices and diagonalization next time. So last thing, just since we've been kind of off in the clouds, just proving theorems and everything for a little bit here, it might be helpful to return to an example since diagonal matrices are really easy to work with. And here's one of the reasons why they're so nice. So let's let T be the linear operator on F3, defined by T of x, y, z. Or, I should write this, I guess, as a list, since we've been writing our lists as x, y's, and z's like across. Let's let it be 2x plus y, 5y plus 3z, and 8z. Okay, let me zoom out a teeny bit more so I can keep everything on the screen at the same time. There we go. Okay. Now, let's look at this guy. So, with respect to the basis 1, 0, 0, 0, 1, 0, and 0, 0, 1, the matrix of T is equal to, well, let's just go through. How do I write T of 1, 0, 0 as a linear combination of these guys? We'll just plug it on in. T of 1, 0, 0, I will get out 2, 0, 0. Okay, so I have 2 of my first basis element and 0 of the other ones. Now I plug in 0, 1, 0. Well, I'll get out a 1, 5, 0. Okay, so I get a 1, 5, and a 0. Now finally, I plug in the last one. I'll just get out an 8, and I'll get out a 3 and a 0, going backwards. So 0, 3, 8, right? Plug in 1 for z and 0 for everything else. Okay, so there we go. This is not diagonal, but it shows that the eigenvalues of T are 2, 5, and 8. So T has the dimension of F3, which is 3 distinct eigenvalues. Hence, it can be diagonalized. Oh, cool. So we can diagonalize this guy. To do this, just find an eigenvector corresponding to each. So to each eigenvalue, I guess I should say, to each eigenvalue here. So 1 for 2, 1 for 5, 1 for 8. Okay, cool. So you can find eigenvalue or eigenvectors pretty easy. You just solve the equation T minus lambda, or TV minus lambda V equals 0, where you plug in lambda is 2, lambda is 5, and lambda is 8. It's a system of linear equations. Nothing too bad. Okay, so we solve for them. Let's do it. One choice. Lambda equals 2. Let's take the value. Let's call it. Let's call this lambda 1. How about lambda 1 equals 2? Let's take v1 to be the eigenvector. How about 1, 0, 0. That is, let me not write it that way. 1, 0, 0. I'll write it across. Lambda 2 equals 5. Let's take V2 to be, I'll even draw little squiggly arrows here to make it clear that these ones are giving each of them. Okay, so for 5, we can get 1, 3, 0. And then lambda 3 equals 8. We'll get out V3 equals, let's do 1, 6, 6. Okay. Cool. Then, if V is equal to A1 V1 plus A2 V2 plus A3 V3, T of V is equal to A1 T V1 plus A2 T of V2 plus A3 T of V3, which we know what T does to each one of these guys. It just multiplies it by the eigenvalue, right? Okay, cool. So I'll get 2 A1 V1 plus 5 A2 V2 plus, 8 A3 V3. Oh, okay. So this lets us do, let's know what T does to any vector V and V since V1, V2, V3 is a basis. That is, it is a list of eigenvectors corresponding to distinct eigenvalues. So it is a linearly independent list, and it is the length of a basis, so it's a basis itself. Okay, cool. This lets us know what T does to any vector. For instance, this makes computing powers of T easy. Watch this. T, let's say to the, let's just write it this way, TK V. Well, this will just be writing it again, right? T to the K minus 1 of, well, we know what T does to V. It's 2A1 V1 plus dot 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 all the way down. Or I won't even do dot dot dot. I'll just actually write it 5A2 V2 plus 8A3 V3. And then that is equal to dot 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 all the way down through. And what we'll end up getting is this extremely nice answer. We'll just get 2 to the K A1 V1 plus 5 to the K A2 V2 plus 8 to the K A3 V3. Oh, cool. So I could compute a billionth power of T applied to V just by taking 2 to the billionth, 5 to the billionth, and 8 to the billionth. I exactly know what's going on here. It's really nice. So, diagonalizing, very easy to do if you have enough eigenvalues, enough distinct eigenvalues. Next time, we'll get into it a little bit more. We'll talk about a few more things. We'll talk about necessary and sufficient conditions for diagonalizability, as well as Gershgorin's circle theorem. So, Gershgorin disks and where the eigenvalues of an operator are located in the complex plane. I'll see you next time.